To prepare for the quiz for this module, make sure that you can name the three main subatomic particles and identify where they are. For example, protons and neutrons are in the nucleus, and electrons orbit around the nucleus in orbitals. You should also be able to describe what subatomic particles are responsible for making isotopes and ions. For example, you should be able to describe that changing the number of neutrons makes isotopes, changing the number of electrons makes ions, and changing the number of protons changes the element itself. So let's start with some problem solving. We'll calculate the wavelength of a photon that's emitted when a hydrogen atom's electron relaxes, so it has a transition, from n equals 5 to n equals 3. And we're given this Rydberg number here. You don't need the Rydberg number if you remember the generalized equation, E equals 2.18 times 10 to the, and that's a negative 2.18 times 10 to the negative 18, and that's joules. And we're going to go 1 over the final state minus 1 over the initial state. Now this negative sign here, this is a convention where the negative energy occurs when energy is released. So that's when we go from a higher to a lower. Now when we calculate this energy, we'll keep that sign convention for now. 18. The final state was n equals 3. So we have a 3 squared here, and the initial state was n equals 2. So 5. So we have a 5 here, a 5 squared. So when we work this out here, we have 1/9 minus 1/25. So you do what's in parentheses first, and then you multiply by this. And in my calculator, I get that the energy is a negative 1.55 times 10 to the negative 19 joules. Again, that negative sign is a convention showing that energy is being released. When we go to calculate the wavelength, that negative sign is dropped. We're really taking the absolute value of the energy, and I'm leaving this in my calculator so as to avoid rounding error. So we have energy is going to be equal to hc over lambda. Now h and c are both constants, and because they are constants, I only have one variable, so this is 6.626 times 10 to the negative 34, and the units there are joules seconds. These are joules. And then C, I'm going to use 3 times 10 to the 8th, and that's going to be meters per second. Now, most of the questions that you answer in my class, you can use the rounded C value. If you're used to using 2.998 times 10 to the 8th for your C value, the system should take your answer. So to solve this problem, first I need to clear this fraction here. So I'm going to multiply both sides by lambda. This is just working out the algebra here in case you're a little rusty. And then multiplying these two things together, 6.626 times 10 to the negative 34 times 3 to the 8th. Divide both sides by this, 1.55 times 10 to the negative 19, and you end up with a lambda. I let my calculator do this work. So my lambda is 1.28 times 10 to the negative 6. Now that's in meters. The question says the wavelength. It doesn't specifically say meters or nanometers. Typically when we talk about wavelength, we do talk about it in terms of nanometers. So I would multiply this by 1 times 10 to the 9th in order to get nanometers, and I would get 1282 nanometers. Now in the homework, I will show you, after you've submitted it, I'll show you a second way to calculate or to solve that problem. There is more than one way to solve the problem, but then here I would report 1282 nanometers and then go back and insert the work if you have time. If you don't, upload your work to the associated assignment. Number 2, a radio station is found at 100.7 on the FM dial. So the frequency is 100.7 megahertz, and that's worked out for you here as a friendlier unit. What is the wavelength of these waves in meters? Now, this is more a physics-like question, but because it is related to our electron wavelengths, we throw it in anyway. So C is going to be 3 times 10 to the 8th. That's going to be equal to lambda that we're looking for times the frequency. The frequency we're told is 1.007 times 10 to the 8th, and that's to the positive 8th, 1 over seconds. Make sure that said positive 8. It did. So I divide both sides by 1.007 times 10 to the 8th, and I get my lambda is 2.979 meters. So that's what I'm going to report here, 2.979. We started with 4 sig figs. We're going to end with 4 sig figs, since that specific problem says to watch your significant figures. So identify the items for an isotope that has an atomic number 16. That means I have 16 protons, and a mass number of 34. Well, my neutrons are going to be my mass number minus my protons. So I must have 18 neutrons. Electrons are going to be equal to protons because we are currently working with electrically neutral atoms. The element name, where I'm going to go to the periodic table and I'm going to look for 16. 16 is sulfur. So the element name, I would type in sulfur, and then the symbol is a capital S. Number 4, copper is made of 2 isotopes. We have copper 63 with this mass and copper 65 with this mass. Given that copper's atomic weight is this number, what's the percent abundance of each isotope? Well, first, we'll set up our problem. Remember that the atomic mass that is reported on the period is 63.546 is a weighted average of the natural isotopes. So for copper 63, I have a mass of 62.9296, and I'm going to assign that an abundance of X. And then I'm going to multiply 64.9278, which was the mass of copper 65, by its abundance, but I don't know what its abundance is. I do know that the abundance of copper 63 and copper 65 must equal 1. So if I assign the abundance of copper 63 as X, then I will assign the abundance of copper 65 as 1 minus X, because I know if I add the two abundances together, I should end up with 1. So now it turns into a straight algebra problem. So I have 62.9296x plus, and I'm going to distribute here. That means I'm going to take my 64.9278, multiply it by 1, and then multiply it by x. Now I am subtracting that amount of x. And that's all going to be equal to 63.546. So now I combine my like terms, combine my like stuff. And what I'm going to do is I'm going to add together, I dropped off my x. I'm going to add these x's together first. Now this x is considered negative, so I take my 62.9296, subtract 64.9278, and I get a negative 1.9982x. And then I'm going to subtract 64.9278 from both sides and end up with a negative 1.3813. Now, because I have negatives on both sides, they're going to cancel out. But I could also look at this as dividing both sides now by a negative 1.9982. So that leaves me with an x of 0.6915. Now remember, we defined this as the abundance of copper 63. So this is the abundance when we're going to be equal to 1. So the abundance of 63 plus the abundance of 65 is going to be equal to 1. That means the abundance of carbon 65 is going to be 1 minus this value. So that's going to be 0.3085. Now, the question specifically asked for the percent, and because it asked for the percent, I need to multiply both of these by 100. So this is going to be 69.15, and this is going to be 30.85. So those are the numbers that I'm going to insert here. And I am not going to put the unit, just the value. I am specifically told that here. Now for additional practice, I want you to work these types of problems many different ways. So click this link for a couple of different ways for how to work those problems. Now let's write the full electron configuration for a neutral atom of vanadium. Vanadium on the periodic table, it's number 23. So when I've done my entire electron configuration, all of my superscripts should add up to 23. Now notice where vanadium is on the periodic table. It's in the first row of the transition metals. And that is, let's see if I can move this over. That is in row 4. So because of where it is on the periodic table, these two elements here fill up 4s2. And I know vanadium is in the 3d shell. So I'm going to go back here and start typing in. I know I want to go to the 3D. Now I'll format that in a second. And now I'm going to count over, because since the transition metals start the D shell, we have 1, 2, 3. So it should end 3D3. Now I'm going to quickly format this with the appropriate superscripts. You have the opportunity to show correctly, so do so. So now let's go over that briefly with the periodic table. I can't show you the entire periodic, maybe I can't show you the entire periodic table. So when we go to create an electron configuration, there we are. Each row gives us a new principal energy level. So hydrogen starts with 1s1. We fill up the 1 subshell, which is an S, with 2 electrons, and that fills up with helium. We step down, and now we're in the 2s. These two elements fill up the 2s, so we have 2s1, 2s2. And here is our p block. So this is row 2, so this is 2p filling up. We step down to the 3rd row, and now we're in the 3s2. These two elements fill up s2, and then we have our p block. Because we're in row 3, this is 3p, and it fills up to 6. We step down, and then we're in the 4 principal energy level, because we're in the 4th row. So this is 4s2. But remember, our D's are ever so slightly more energetic than our S's. So this is 3D. And we count over 1, 2, 3. And that's how I get the 3D there. Number 6, we're going to identify the subshell in which the electrons where the quantum numbers are found. And we're going to type in the principal energy level and the orbital. Well, I just wanted to draw this out real fast. So if we have our N, so our principal energy level, and our N is going to be 1, 2, 3, 4. Then we have these orbitals. So our first principal energy level only has an S. Well, actually, they all have S's, so I'm just going to fill those in. Our second principal energy level has a P, and that's where it stops. 3 and 4 also have P's. 3, you add a D. 4 has a D, but it also has an F. Now, when we look at our L values, S is an L value of 0. P is an L value of 1. D is an L value of 2, and F is an L value of 3. So when we go back to our problem, we're looking at N equals 3 and L equals 2. So let's find it on our chart. When N equals 3 and L equals 2, then we're looking at the 3D. So that's what I'm going to type here, 3D. So now I'm looking at N equals 4, L equals 3. So here's N equals 4, L equals 3. So this is going to be our 4F orbital. And the last one, we have N equals 2, L equals 1. So I come down to N equals 2, L1, we have a 2p. So that's what gets entered there. And finally, number 7. These mole calculations are going to come back in just about every module because this is a very important concept. So I'm going to start with 44.8 grams of rhodium, and we're going to calculate how many atoms of rhodium we have. So I start here. I start with what I'm given, 44.8 grams of rhodium. Now, rhodium is the plating that's often used in white gold to make it look whiter because white gold still does have a yellow cast to it. Rhodium is found, let's see if I can increase this just a hair. Rhodium is number 45. It's found right here in the middle, and its atomic mass is 102.91. Now, 99% of the time in here, when you see grams, you will need to convert into moles. Again, that's 99% of the time. That's most of the time, but not all of the time. So I'm setting up this dimensional analysis so that my grams in the numerator will cancel with my grams in the denominator. Remember, we use units as if they are factors. So now I have moles of rhodium, but the question asked how many atoms of rhodium. So now I use my expression 6.022 times 10 to the 23rd, and oftentimes I will drop this 2 just because the way I learned it was 6.02. You should not see a difference in your grade if you drop that second 2. So here I've converted my grams into moles. I've converted my moles into atoms. So now I do this arithmetic, and it is important that you enter this into your calculator correctly. You will need to use that you're going to be looking for an EE, or you're looking for EXP, or on some calculators you'll have a button that looks like this. So these are the things you're looking for. A lot of times they're going to be a second or a shift on another button. But in order to perform this calculation, it's 44.8 times 6.02 times 10 to the 23rd, and then you divide it by 102.9. And you should end up with a value of 2.62 times 10 to the 23rd atoms. So come over here and enter that. Make sure your formatting is correct. So select your exponent and give it a superscript, and then type in atoms.